Good morning, everyone. Welcome to this session and to the last day of the week. Happy Friday. We are winding down week 5, and we have 1 week left before we get to finals. And I hope you are all doing great and getting ready for the last lecture of classes next week and for your exams. So before I get started today, I want to talk a little bit about why I didn't report on your warm-up question last time. That was because Osbol, the platform we use for having to post material, was down that day for a good portion of the day. That had happened on Monday also. And so I had sent out an email or I used Blackboard to reach out to you. And so I had tried to get material that was recorded before, and then homework 7, which you are working on there. Osbol is back. It is not entirely clear to me if we are going to have no more issues. I'm hoping that it will not have any issues, and so we will continue. If that happens, watch out for things that would come from Blackboard and don't get said, what happened to Asifa? Why is he using Blackboard now? That might be because Osbol has been working perfectly fine for us. And the reason for why it is has been down has to do with something that is a little bit outside of our control, and the person who runs or developed and runs it is a little bit outside of their control too. And so let's see, but be ready for having to get communication from me through Blackboard. The other thing I have done is went to the lectures and slides and the video recordings we have been having on Osbol and moved them to the public page of the website. And you never had a need to go there. We know of its existence. We've used it for a few things, but we never used really the public portion of the web page for anything other than having in the beginning of the semester to have the syllabus out and so on. So I will post a note today to just remind you where to go. But that one where we have schedules and the dates where a topic was discussed and what material is available is one way for making this one also there. So in some sense, everybody gets it now, which I'm happy with. I don't have any problem, but that is also an alternative for us. At least I don't want you to be looking around for things when the time comes to revise. You look back things and get ready for your final exam. And hopefully there are also other things that you may want. And so I don't want you to be losing them. And so they are there. So if you go to the public site of the webpage, the course, the table, the thing that we call schedules, now has a listing of what we've been busy all year long. As you very, very well know, when we were doing things in person, I was using the document camera and we were writing things, and you were very patient with me and struggling with my poor use of that camera every now and then. But we agreed eventually that it would be helpful if I scan and post them. So you would get those also there. But you have been also good at taking your own notes, so you probably don't have to go too much back to them, but they're there. But the slides, which are easier to see now, are there on that public web side of the web. Today is Friday, which means this is a day where we trade. In old days, people would go to market, and so they would take their thing and then they would get something else in return. Fridays had happened to be a day where we trade, you submit, and you get something in terms of homework. And so I know you are all almost ready. Some of you are just finishing up on one problem or two, or something like that left. A good number of you have already submitted. But just so you know, or as a reminder, today is the deadline, and I would like everybody to submit before the deadline, while Osbol is still active, and still on Osbol is where I am wanting to do. If anything happens, I'll let you know how to move to submitting on Blackboard. But for today, the way things are, I'm hoping that it will be fine. So go submit on Osbol homework 7. Homework 8 will be out later today. And I don't want you to think about another homework before you have submitted your own. So let me use the rest of the day to decide on how homework 8 should look like. It will be focused on reducibility, the thing that we discussed in chapter 5, and maybe just one general problem on the kind of thing that we are touching on now. Homework 8 will be out now. It'll be the last one. It'll be due exactly a week from today on the very last lecture of day on May 1st. Next week is, generally speaking, a week of reviews. A week of reviews for looking back at what the course had been and preparing for the final exam. The final exam will be released on May 1st, that Friday, and we'll use Wednesday's class especially to prepare, and that kind of lecture. Monday's lecture would be a review of general kind. There is a little bit of a portion that I will probably need to borrow a bit of a time on Monday, and that will be a continuation of what we have started to do now. All right, that was kind of the beginning, and I am hoping that everybody is in good shape in terms of submitting their homework and getting ready to have a weekend that's free of homework. If you are very curious, this lecture is going to end with a big, grand, open question to everybody, not just computer science, but the top people and with their top thinkings have around. There is one grand open question in theoretical computer science. Those of you who need a challenge and somebody may want to think about it the weekend, that's how this lecture will end. We'll end with an open question that nobody knows the answer for. Okay, last time when we started the discussion, I asked if what analysis would bring to mind. That report didn't come because Osbol was down. But there were very interesting answers. There is no right and wrong answer, by the way. So for this type of questions that I ask you, but there were some very interesting things. Interpretation, examination, break down and connect. What data did they use? All sorts of interesting answers came about, and sometimes there is a connection somebody has made with what that word would mean. And that word was important for us, but the breakdown and connect kind of thinking was exactly what I was trying to get to. If you were taking a class in numerical analysis and that came to mind, that's a perfect answer, because that is exactly what we're busy with, and the word analysis right there in front of that thing. And it is used in many ways in different contexts. So I was not after a particular answer, it was more of to see where your mind would go. So if I would like to do something similar today, I would use the word complexity. And you know what I mean, you know where we're headed. We have made the case for what this is the third part of the book in a way, and we just want to get some introduction. This is not the main part of our course, but we are learning about complexity. So in a way, we know the context for it, but it is just like analysis is a very commonly used word, and we use it in different senses, all of them being right. Complexity is one of them. In fact, it is even more so. And depending on who you talk to, when people are experts in certain areas, it will be a big word in telling a lot of things at the same time. Now, I'll turn this question around to you, and you would participate. When you hear the word complexity, what comes to mind? One word, two word, a phrase, anything like that would be just fine. Classes is not included in the question. Complexity. Classes is a very nice word, a very friendly word. We know what classes are, and we are very busy. We like our classes that we take. That's not what I want to have. Complexity, just complexity. When you hear the word complexity, what comes to mind? So because everybody's on board now, I'm not going to type it up, but just in case somebody just shows up a bit later, I'm going to write the question on the chat board. When you hear word complexity, what comes to mind? All answers are welcome. There is no right and wrong answer, but it is a deep question in some ways. And so let me see what you think. We're going to get started now with what we want to do for the day. Complexity theory, we boiled it down in terms of what we want to learn as an introduction, and what the book focuses on for its third part, devoting a good 4 or 5 chapters, is about the investigation of resources. Computational complexity is what I'm talking about now, because I've asked you a question and I don't want you to be thinking complexity outside of computational complexity. We are in computational complexity theory, but let's call it complexity theory, is about investigation of resources required for solving computational problems. And the resources that we are concerned about are time, memory, and sometimes we have other resources. And out of these 3, our introduction would be on just time complexity. In last lecture, we saw how time is measured. And then we started discussing about classifying problems. In the very last lecture, slide we had then said, if we build our tents large enough, then we will be able to classify problems in a nice few neat classes. And that is what I would like to do today to get us to that place. And so let's begin by having to talk a little bit about complexity relationship among models, because last time we saw that when, unlike computability theory, where things were not so much dependent on the computational model because they were all almost about the same, they were doing the same thing in terms of decidable language. Once we are decidable, the computational model we use would determine the complexity relationships. And so we saw a few examples. So we are going to be going through 3 computational models now, one at a time, and then see what their implications would be. All of them are about Turing machines. And so the first machine we'll look at is a familiar one, single tape Turing machine. The second one we'll look at will be multiple tape Turing machine, also familiar one. And then the third one we'll look at will be non-deterministic Turing machine. We know non-determinism in a general sense, and we did get in a very exciting way introduced to what non-determinism was already when we were talking about finite automata, non-deterministic finite automata. And so let's see what these ones would mean in terms of complexity relationships among models. Let's start with single tape. So I'll think of like single tape Turing machine as our baseline, our de facto, and then see what happens if we were to move to multi-tape. What happens if we were to do not single tape deterministic, but non-deterministic. That's how we will approach this. So single tape deterministic Turing machine versus multi-tape. Here we have a result that says about how these things are related to one another. If you remember our keyword last time, the thing that we wanted to see what comes to mind was analysis. So if you, and now we are doing time complexity. So what we are busy with, I don't want you to lose track of things. What we are busy with is to break down things and look at what time it would take for some decidable problem on a Turing machine for it to be solved. That time we have found a function, it takes the input in some encoding of it, and we take that length, and the function that we call running time will take that, and it will be a mapping from natural numbers to natural numbers. So we get a number in some ways that is described as a function of the input length, and that was our reserved denotation for it is the letter N, and so that's the input size. And though we give the running time in terms of that, that was how we were going. And so what we will be showing as results now will be things that would relate time complexity-wise, time-wise, what it would be when we have things on a single tape machine versus a multi-tape machine. On the next one, it will be 2 other things, single tape deterministic machine versus a non-deterministic machine. So I'll state the result, and then we will talk about how we will get there. And that the get there part is sit down and count and analyze that time complexity to arrive at this big O notation. So the result says, if we have a function Tn, where Tn is interesting, right? It's more than just linear, where Tn, the input, last time James asked a good question when I was talking about that. Our favorite example, 0 to the k, 1 to the k, where k is greater than or equal to 0, we saw a couple of examples for solving it. And so we devised a clever algorithm that says if we use 2 tapes, it will happen like this. And then he asked, can we go further and have more and more tapes and then just solve it in constant time? And so I had to think about it a little bit, but to go below what would be the input lengths would be something that's untraditional. There are people who do sublinear algorithms, but you need to read the input. And so that's what this one is saying. So we've got at least an algorithm that is devoting the time to at least read the input is what this Tn is greater than or equal to n would mean. That's interesting, non-trivial case. So let Tn be a function, and then every Tn time multi-tape Turing machine has an equivalent square root of t times single tape Turing machine. If you remember, when we talked about Turing machines and we devoted an entire lecture on it, we saw all kinds of variations of it. The end of the story was these variations, including having to have more tapes, doesn't add power to the Turing machine, so we're fine. Why? Because we can simulate the thing that a multi-tape Turing machine can do with a single tape Turing machine. So that much we knew. What we are learning now was if we actually care to find out how much time it took when things were done on a multi-tape compared to what we would do in a single tape, how much would that simulation cost us now? And so if Tn was the time that the multi-tape Turing machine, which is more powerful, which is more equipped with extra tapes, would do it in Tn, then our favorite single tape Turing machine can do it in square of that time. Is what this result is saying. So the idea for this one will take us to the lecture that we talked about that time when we did the simulation. And I'm going to use this one now, and we're going to use one more example like this, where we would actually go back to that lecture and borrow a slide and see what the simulation, how the simulation looked like. But the idea is to be carefully looking at what the simulation did, look at the steps, each of the stages. We know how Turing machines, at least the way this nicely does in the book, is describe them in some high level, and then we go through the stage and argue for how much time it would take for stage 1, how much time it would take for stage 2, and so on, how many repetitions we have. And then finally we say this is the time the algorithm would take, and we give an expression in terms of big O. That's what we would do. So that idea of having to simulate a multi-tape Turing machine using a single tape Turing machine, which happened to be called Theorem 313 in the book, is to go there and then to find out what those times would do. So our next slide will take us to that simulation. And I want you to keep this one a little bit in your mind. So you've got something that was T of n, T, let's call it T. And then that was what the multi-tape Turing machine was taking. We can do it in T squared. So even if I don't remember, if I were in your shoes, for example, okay, I prepared these lectures, I know, I have read, and you know, I do research, so I know this. But let's say I was not, and I was just one of you and in the class, and if I don't remember anything about how that simulation worked, and if somebody tells me a result like this, something would come to my mind. So there must be something this one is doing this many times, T times, and each time it's doing T work, because what's what the single tape machine would do, then the quadratic would come to picture. So there was one thing that was able to do it in T time. Here is another thing that is trying to do, will do it in T squared time, will tell me the simulator now has got T steps to do in each one of them. It probably would not need to do more than T, and so I can multiply T by T to get T squared. That would be my guess. And I would be right. And that's how actually the simulation works. So here is a slide borrowed from the lecture on March 27th. If I have picked the right date, I think I am right, but this is when it happened. And so we were seeing how a multi-tape, the M and S are multi-tape and single-tape Turing machines now, how the multi-tape Turing machine, thanks to its multi-tapes, would have got different heights and different things. And the single tape would just put them in one big long tape because that's all it has. And it would separate them with these hashtags, and it would put a dot on something like that. When you remember how this story goes. And so the story is repeated with this simulation idea, what it was doing with its K tapes. And so if you now recall what I told you and try to see what the single tape Turing machine did to simulate this moving its head and putting these symbols, it will not need more than T time, whatever the multi-tape Turing machine was asking it to do for each one of the things that it has to do, for each of the steps that is. And because the multi-tape Turing machine was doing this using Tn time, then, and every time the single tape machine doesn't have to do more than what the multi-tape Turing machine was doing, then I can bound it by T squared. That's essentially what the idea is. And because our goal now here is for get introduction, I'm not going to bother you too much by the details, but I think intuitively you got why that idea, that proof would work. We took care of one. So we are in this business now to show what computation models influence time complexity. We took care of how we can go from single tape to multi-tape, and the result we got was neat. Tn in multi-tape would be done in T squared time in single tape. And if you are curious, you might wonder, actually, you didn't tell me how many tapes the multi-tape Turing machine had, and it won't matter. It won't show up in that equation because it will still be in T squared, just in case you wondered. Okay, now let's go to the version where we are going to take a deterministic machine and compare it with non-deterministic Turing machine. This one is interesting because now we will have to agree on how we are going to find what it means to measure time. We were fine last time when we talked about runtime. We said take input. We'll call it the length of it. It will be called n, and the function that will take it, the worst time it will take for that algorithm when it is described, is what we will call the runtime of that algorithm, and we called it f of n. That was deterministic. So we know stage after stage after stage what the computation would look like, and so there wasn't a lot of things to agree upon. That was what we did, except that we do worst case and we use all notations. That was basically what we had to bring up. Non-determinism is a different story, and you remember both from even automatas, finite automatas, and in Turing machines, that non-determinism has got an idea around it that could be best understood in terms of a tree. And so you've got different routes this computation can take, and then we would arrive at an accept if one of them leads to an accept, but there may be several options non-deterministically when those choices are made where things could reject, but that's not the end of this. Just because we found one branch and traced it and got a reject does not mean the membership question we were investigating would be a reject. No, we may have another one that would lead us to accept. That's actually why non-determinism would help us have more things to come. Now, I'll be careful. When I say more things to come, we will actually find out that result in Turing machines. Now, in finite automata, the power to express changed, but the language was the same. In that sense, they were not more powerful, but they are powerful in the sense that we've got more non-determinism, basically, in how the computation works. So the agreement we'll have now will be to say, if we have n to be a non-deterministic Turing machine, and it is a decider, we have a computational problem to solve. That's what it means. Then the running time n will be is a function from natural numbers to natural numbers, where f of n is the maximum number of steps that n uses on any branch of its computation on any input length n, as shown in this figure. So there are a number of any here. So when it was deterministic, it's just the worst case time. But now when it is non-deterministic, among the things that could come to an end, like for example, there is a reject very early on. No, that's not the f of n. The f of n is, the runtime is the maximum, the thing that you could see in the entire branch. There may be some branches or some parts of the computation that would end sooner than others, and so we take the one that would take the longest is what it means. So that is what our definition of runtime would be for non-deterministic Turing machine. So we agreed on a definition. Here is the result. The result says if we have a function Tn just like what we before, then every T of n time non-deterministic single tape Turing machine, okay, the one that has got more the power, what will our single tape deterministic Turing machine do on it when it does that simulation? It will do this job in a time that is 2 to the power of T of n. That means we're now going to need exponential more time. In the case when we went from single to multi-tape Turing machines, we just needed to square the time. Now we needed a lot more, and then that is because there is a lot more that the non-determinism has offered. And so that will be a major result. The reason, or the proof for this, that it takes this month, will also take us back to that same lecture on March 27, where we looked at Turing machines, the different versions that they have, and non-determinism was introduced there. What we did then was to simulate what a non-deterministic Turing machine would do, and then we argued for the very basic computational structure that you saw in the tree, and we said we'll explore this tree and do a simulation in that fashion. In fact, now that I've told you my guess, what I would do if I were in your shoes to argue for why single to double or multiple tape machines would take from T of n to T squared of n, because I would then argue for each tape, I would need at most T of n, and therefore it will be squared. Now I have more things to go through, and so there is exponentially many different things that I have to explore when I do this simulation, and therefore it becomes 2 to the power. That will be my intuitive interpretation of how the simulator for the non-deterministic Turing machine using a deterministic Turing machine would need that much resource, that much time, would be explained in this way. And it would be right again. And so here is a recollection, a slide borrowed from March 27, and here how the deterministic Turing machine was taking a trip and then it was simulating it, and it borrowed something. That simulator actually borrowed something, because now it said, okay, I know I am a Turing machine. I am allowed to have more tapes, and I still will be called a single tape because I can be simulated by another single tape machine. So why don't I allow myself to have multiple tapes and do my job a little easier so I can track and things like that? If you remember that discussion, that's what this D did by having three: one for the input tape, one for the simulation, and one for the address tape to keep track of things that happen on the tree. If you carefully then try to analyze what that simulator was doing, you will not have a lot of trouble seeing that it would take exponential time. So the result would follow. So I think this was nice that we had it in the form of slides. I can just plug in as I need them, except I changed the title and call this one an old side. Otherwise, it's exactly the same slide we saw in 327. And this is also a good way when we get the chance to review things for your finals and kind of wrap up the course and make sure that you can defend your way all through all the topics. To see these connections is actually a very nice thing. At that time, our job was to see the equivalence between Turing machines. Now we are tasked with having to account for it. We are now going to sit down and say, how much did it cost? Okay, go step one, step two, step three. And so we did do that, and we can give analysis of it, time complexity, the time requirement for it, and we found out, or we can prove that it will take 2 to the power of the order of t of n time for it. Okay. So what did these results, the two results we just saw, single versus multiple tape Turing machines and deterministic versus non-deterministic Turing machines, they illustrate an important distinction. The two distinctions, the important distinctions, are the two bullet points right there below it. On the one hand, we saw that at most a square of the time that was needed for the multi-tape Turing machine was enough to simulate it on a single tape Turing machine. Square was the word there. And so we will be a little more generous, and generally we would have seen a place where conversions from one computation model to another computation model could be accommodated within something that is polynomial. That was when it is deterministic single tape and multi-tape Turing machines. This is one nice result. So jumping up and down between multiple tape and single tape machines, I shouldn't say up and down, left and right maybe, or something like that, back and forth. Between these two can be absorbed, can be incorporated with something that is only polynomial difference. On the other hand, we saw that at most exponential difference between the time complexity problems that are on deterministic and non-deterministic. So there is a huge gap or difference between these two, and these two examples illustrated it. So for this reason, we have, now we're building our tent. The tent we talked about last time, build it large enough so that we can put many things together. We're there now. We are all getting very close to actually nail some of those things on our tent and then have some occupants coming in. Okay, so for our purposes, polynomial differences in running time are considered small. If you are a computer science, n squared and n cubed and n to the power 4, they are all the same family. Somebody else would say, if you were making money, and if you say, I, have what I was making squared, and next year I got something that is cubed of what I get, you will know what I mean. That will be a lot of difference. But we will consider those differences small, whereas exponential differences are considered large. And so this time division between classes now, would we say, is it polynomial? Is it exponential? Is the difference small that I can just be okay with it? Or is the difference big so that I will speak about it and put it in another class, is what it would mean. So this separation between polynomials and exponentials rather than other refined classes of functions is good. And there are many reasons why it is good. First, there is a big or dramatic difference between the growth rate of a typically occurring polynomial and a typically occurring exponential. For example, an n cubed and 2 to the power of n. There is difference within polynomials how fast they grow, but if you compare the growth rate, when things are polynomial and the things are exponential, it's very big, it's dramatic. And that is what is one of the reasons why this distinction is a good one to make. The other thing is exponential time algorithms are, typically they would arise when we solve problems by trying everything, exhaustive search. So you've probably encountered enough of examples in your own studies so far, but when there is a computational problem to solve, you can think of it as looking for a solution and there is a search space. And when you don't know any better, and you would be surprised, sometimes people do actually do that, you try everything. You try everything and try to find the best one. That usually is not a good idea. And sometimes we don't have any better thing to do than that, but exhaustive search, it's also called brute force, would take exponential time because you've got many, many things to try out. Sometimes when we know the problem well enough and you're students of good theory of computation like this, or you've even taken the time to understand the problem, then you may actually find something in it, some structure in it that would reveal a polynomial time algorithm that is not about trying everything, but you'd be a little more clever. And so the distinction between polynomial and exponential would also mean understanding a problem well enough to come up with something that is not immediately available in how the problem was formulated, but required a little bit of insight and cleverness. And that distinction now becomes important. And you probably have seen examples, but I'll mention one example today. I should also have that caveat. There are problems for which we don't know anything better than to try everything exhaustively in a brute force fashion. Okay, that was reason number two. Reason number three, if we were to come to all computational models that are reasonable, and by reasonable I mean things that are not fanciful and things that can be done in relatively fast, then models are polynomially equivalent. I can change, just like you saw the single tape and multi-tape one. Something you could do in multi-tape in t of n time, you could do in t squared time using single tape. And that's polynomial, they are polynomially equivalent. So these three reasons, so another way of saying the third point will be to say one of them can simulate the other with only polynomial increase in running time is what I mean. So these three reasons make that distinction between polynomials and exponentials interesting. So meet the first class of the classes that we would meet today. It's called the class P, and the P there is for polynomial. So this is now a class of languages that are decidable in polynomial time on a deterministic single tape Turing machine. Last lecture, we introduced that guy called time n to the power of k. That is the class of language for which there is the runtime is n to the k, where k could be 1, 2, or whatever it was, right? And so our regular language, the 0 to the k, n to the k, this k is different. Was, for example, found to be, if we were to use a single tape machine, n to squared, and we used to multiple tape n log n, but we said it will never be able to do more than n log n. But if I take all of the problems that are linear, all of the problems that are quadratic, all of the problems that are cubic, and put them in one big family, that tent is now called P. And so this is a class. And this plays a central role in the theory of in theory. Let me put it the right way. Theoretical computer science, so theory of computation, right? And it is important because P is invariant for all models of computation that are polynomially equivalent with one another to the deterministic single tape Turing machine. And because P roughly corresponds to the class of problems that are realistically solvable on a computer. This is a connection now to, or this point is a connection to problems that are not in P, and most of the problems that are in P can be called fast. In fact, people who do theory would call algorithms that are in P fast, and they won't even worry too much about what the power in n is, squared, cubic, and so on. You would not call an algorithm that takes order of n to the power of 6 a fast algorithm, and there are very rare. We usually are on a small number when we actually talk about problems, but things that can be solved in polynomial time, another name for them is fast, and they naturally correspond to a class of problems that are realistically solvable on a computer. Okay, I'm going to go a little bit fast and give you a couple examples. We will see the other class that we will look at today that will introduce that's not a P, and there I would be slower or faster even in giving you examples. But problems that are in P are problems that you have encountered in your courses most of the time. Most of the problems that you have worked on would be in this class. So I'll give 1 or 3 examples, and for one of them I would also show you how you would do the runtime analysis a little bit. And then for the other ones, I will go a little bit faster. So the first problem that is in P that we will see is to, given a graph, a directed graph, is there a path from S to T, source to target? Can I go find like this and then say, there is a path, there is no path? That's called path decision. A directed graph has a directed path from S to. This problem is in P. I can solve it in polynomial time is what it would be. Here is my proof. What do I need to do? What do I need to do to prove that the problem is polynomial? Well, I have to give the Turing machine that does the job, go through the states, make sure that I count them, and then show that that runtime is polynomial. That is what it means to prove that the problem is in P. And so in this case, you have seen a lot more involved problems, a lot harder problems, and try to, as a decision problem, and design Turing machines for them. So this will be a piece of cake for you to show that if I have a graph, it has got a source and a target, and this is the encoding I have. Do I have a directed path with nodes S, that connects S and T? So you would start with, mark on a node S, and then you would repeat until no additional nodes can be marked, and you would scan the edges of G, and if you find an edge that goes from the marked node A to an unmarked node B, you mark B, so that means you're making progress, and so you keep on doing this, and when T is marked, then you arrived home, and so we will say accept. If you cannot get to T by doing this scanning and following these links as they go forward, you would say reject. And so the algorithm is not all that difficult. And so you've marked in. What I want to show you is how you would actually argue for why this one is in polynomial. So you can look at stage 1 and 4, and you can see them. You don't need to do more than once. You just need to do these things once. What is repeated is in what is described as step 3, and the repetition happens in stage 2. And so how many times are you doing? You are repeating this until no additional nodes are marked. And we say there are m nodes in the graph, that means you're repeating it m times. And each time you are looking at what you would do with whether you have an edge that would take you from A to B. And so that's the scanning you do. So you have stage 1 and 4 that are executed exactly once. Stage 3 runs at most m times the number of nodes. And so the total number of states you need for this Turing machine to finish will be 1 plus 1, that is the first and the fourth, plus the m you have. So that's linear. And then the next thing we need to argue is what is happening in stage 1 and what's happening in stage 4. And you can see that that will take you, it's very easy to see that you can implement this one in linear time in the size of the graph that is. And so you have polynomial m plus 2 stages to do, and in each one of them you do not need to do more than m, and therefore this algorithm in general would be just m plus 2 times m. That will be the maximum you would do, and that's all you have. And therefore this is not only polynomial, it's actually a small power polynomial, and so you can prove it that way. Okay, just like this, we could give more examples, and I'm going to give 2 more examples. One of them has to do whether 2 numbers are prime relative to each other. And if this problem was formulated in this way, and you were trying to do whether they are relatively prime to each other with respect to each other by looking at all of their factors, you now are in the realm of doing things using exhaustive search by brute force. And that means you would probably be felt to think like this problem is not polynomial because you've got exponentially many things to explore if you didn't know. But we know there is a better, or there is another solution, or there is a result we know that could help us find a faster algorithm, and it's an ancient one. We talked about this one, in fact, when we were talking about Turing machine definitions, and I mentioned Euclid at that time, and so the greatest common divisor, and so you remember your high school math there, how you can find that one. If you do that, then it can be done in polynomial time. This is an example to show you that there are problems that when we have understood about them enough, we can come up with algorithms that are faster than what an immediate one, and naive one would have suggested that would require us to do exhaustive search or brute force, and therefore it becomes exponential. That's not the case, and this is a very good example. I'm going to give one more example, just because we have worked with context-free language a lot. And this is one of the things that this course was spending a lot of time on understanding it. And so we know context-free languages are decidable, right? We know that much, but what are they polynomial? And the answer is positive. So we can, every context-free language is a member of P, the way we defined it now. And the proof for this, which we don't need to go into detail, but if you're interested, you can look at in the book, would bring some very nice use of something we introduced when we were talking about context-free language and context-free grammars. And we talked about context-free grammars and their Chomsky normal form, where things would be. And so there was a number that we associated how many steps would be needed when things are in context-free grammars. That becomes a clue now for having to devise an algorithm that would be in P. Just like the relative prime example I showed you earlier, if you were to go about thinking about this problem to show in P, it would not be immediate. But once you have discovered a relationship, like writing it in Chomsky normal form, and something called dynamic programming. This is a computer science basic, one of the algorithmic paradigms we have when problems could be solved cleverly if you build them bottom up. So you know how to solve the pieces of problems and combine them, and combine them until you get your solution to the final thing. That type of programming is called dynamic programming. The term is historic. Sometimes these terms are not very helpful in revealing what they really are, but this is a way to build up solution by looking at solutions for subproblems, basically. And so that would be an example of a problem that is polynomial. All right. It's 10:51, so I have finished P, and so now I'm going to get to class NP. So here's a place where you probably will stretch your arms to just get a break from what I'm doing. So we finished one class, and we're going to introduce another class. Just like we did P, now we are going to do, P was for polynomial. Now you would, if you are like the kind of person who would say, you've got intuitive feeling where this is headed. So we are going to be headed to problems that are not polynomial. That would be the first clue. If they were not polynomial, I argued for a long time now to say the other class we're looking at would be things that would take exponential time. And you would be right. But then we would want to be clearer on how we will go about this one. So this would require us to say like this. Okay, for the real prime problem, or the context-free grammar problem and things like that, you said if you understand the problem well enough, you do not have to do exhaustive search. You do not have to do exponential exponential runtime. Is this true that then I can find that kind of thinking for every problem? And the answer is no. There are problems for which we don't know how to get polynomial time. We just don't have anything better than living with what the exponential time would give us. And for that reason, we want to classify problems now in a way that would help us say something more. And that something more is called verification. Verification would say like this. So I give you a problem and you give me an algorithm for it, a Turing machine in polynomial time, and I'm happy. There is a decider, it runs in polynomial time. I will say the class belongs to P and we'll be done. We'll go home. This one would say, no, there are problems that I cannot put it that way, but can you do one more thing? If you ask me, I don't know how to do it in polynomial time, and it would probably take me exponential time, but I give you an answer. I give you a certificate. I give you an evidence. Can you verify whether that answer that I gave you to this question was right in polynomial time? When you can do that, then the class gets a name. And so the verifier now would be called polynomial. It's verifying. It's not deciding it, but it is at least verifying it. So that's the definition. A verifier for a language A is an algorithm V, the V is for verifier, where A is the input W, and V accepts this W and takes this certificate C for some string C, and that will be the verifier. We measure the time of a, this is the definition. I did not go any further, so there is a period there, so I should stop. So that's what A is, that's a language. Now we measure the time of a verifier only in terms of the length of W. So a polynomial time verifier runs in polynomial time in the length of the input. If it can do that, then it's called a polynomial time verifier. A language A is polynomially verifiable if it has got a polynomial time verifier. Fair enough. Now we'll define another thing. We will call this class NP. NP is the class of language that have polynomial time verifiers. So we've got a result. A language is in NP if it is decided by some non-deterministic polynomial Turing machine. So there is a gap. I just told you now about verification, but that NP, you might have wondered what the N was coming from. And that this is a fairly important result and deep result that says those type of problems for which you can verify, it means there is a non-deterministic polynomial Turing machine that would decide them. So if you remember how the runtime was defined for deterministic and non-deterministic, I showed you a tree and I showed you what it means to have a runtime for a non-deterministic one. That time is polynomial when it is non-deterministic. That class is NP, the same class that we have a polynomial time verifier. So we'll define now this class called n time, just like we did time last time, we would call it n time. This will be the set of language decided by an order of Tn time non-deterministic Turing machine. And the whole class now, when we have all the case included, will be called NP. So we have NP seen in two different ways now, one in terms of verification and another one in terms of polynomial time on a non-deterministic machine. And these two things are the same. And so we'll call that class NP. We've got a lot of problems that are in NP. I'm going to give one or two examples. We have 4 minutes. And so I'm going to give one or two examples, and I'm not going to show you to prove it's beyond the scope of what we want to do. But at least know there are some problems for which we do not have, unfortunately, polynomial time solutions. And these problems would be problems that you would easily understand. It's very surprising in some ways. Most of the NP problems that we know that do not have polynomial time solutions, they are not that difficult to state. You can pick a friend and tell them, you know, in 3-4 minutes, you can give them some definitions and so on, and you will be done. And so they would know what the problem is. The problem is we don't have a polynomial time solution for it. So a click in a graph is where everybody's connected with everybody. A k-click is a click in which you've got k members. If I have a graph and somebody gives me k and g is an undirected graph, does it have a click of size k? That will be what this click problem is with all caps. We do not have a polynomial time algorithm for this. And then there is this subset problem that is a little lengthy here when it is described, but you've got a set that has got k elements, and you are going to find a subset of L elements from this k, where the summation of all of these subsets is going to add up to a certain number t, which is part of your input. That's called a subset sum problem. We do not have a polynomial time algorithms for this. Now, this is the place where I'm going to tell you the big, grand open question in theoretical computer science. P is the class of language for which membership is decided or can be decided quickly in polynomial time. NP is the class of language for which membership can be verified quickly, that's in polynomial time. Are these two classes the same, or is one contained in another? We do not know. This is an open question. People have said, I know the P versus NP question. They have given an answer for it this way or that way. It all failed. So it's an open question, but the conjecture, most people believe, including myself, P is different from NP, or the egg-shaped figure that you see on the left is a reality rather than the thing on the right. But the two possibilities still are open, and this will be your, okay, I was kidding when I say solve it over the weekend, but this is an open question, and this is what I want to stop today. All right, any questions? We are just 1 minute before we get done for the day. Any questions for me? was everything clear? Okay, that is yes, that was perfect. I got a few yeses, and so that's great. All right, I'm going to stop here and have a nice, great weekend, and make sure to submit your homework 7 and look out for homework 8 when it goes out so that you can jump on it very quickly, and it will be due next week. Next week we'll do review, and I will see you then. Take care.